Imagine attempting a full inventory of everything that exists in the universe: stars, galaxies, planets, dust, gas, clouds of plasma, and all the visible components that shape the cosmos. Now imagine that, once the counting is complete, roughly half of all the expected ordinary matter has simply vanished, not destroyed, not hidden behind dust, not locked inside black holes, but spread somewhere you cannot see and cannot detect. For more than 30 years, astronomers faced exactly this riddle. According to precise cosmological measurements, especially those derived from the cosmic microwave background, about 5% of the universe should consist of baryonic matter: protons, neutrons, electrons, and the atoms they build. Yet, when scientists tallied up all the baryons seen directly, they could only account for about half of them. Half of the matter that forms stars, planets, and galaxies was missing. This puzzle, known as the missing baryons problem, became one of the great enduring mysteries of cosmology. It was a gap in our understanding with enormous implications for galaxy formation, structure evolution, and the heating and cooling of gas on cosmic scales. But the story does not end with the mystery. It ends with a discovery, one enabled by a phenomenon that only recently entered astronomy: fast radio bursts, or FRBs. Before diving into how the mystery was solved, we must clarify what is meant by baryonic matter in cosmology. The term refers to all matter made of baryons particles such as protons and neutrons. This category excludes both dark matter and dark energy, which together make up the majority of the universe. Baryonic matter is the ordinary matter that forms everything we can directly observe: stars burning hydrogen in their cores, planets orbiting suns, interstellar gas drifting through galaxies, and the dust grains from which new solar systems emerge. The fraction of baryonic matter predicted by cosmology is extremely well understood, based on early universe physics and nucleosynthesis. But when astronomers attempted to find these baryons in the present-day universe, adding up all known reservoirs of gas and stars, the numbers came up short. Very short. Roughly half of the baryons were missing from view. Over decades, astronomers catalogued every known component of visible matter: stars in millions of galaxies, neutral hydrogen gas, ionized gas in galaxy halos, hot plasma inside galaxy clusters, dust and molecular clouds. Still, these components amounted to only about 50% of what should have existed. The leading hypothesis was that the missing baryons were hiding in a phase of matter difficult to detect: a hot, diffuse plasma threading between galaxies, a kind of invisible scaffolding linking the universe into a vast structure known as the cosmic web. But observing this gas was extraordinarily difficult. It did not emit light strongly. It did not absorb light in ways easily detectable. It was ionized and diffused, stretching across millions of light years. To find it, astronomers needed a new kind of probe, one that could reveal matter not by light, but by its effect on a signal passing through it. This probe would come in the form of brief, intense flashes of radio energy from distant galaxies, fast radio bursts. The first fast radio burst was discovered in 2007 in archival data. It lasted just a few milliseconds, but carried more energy than the sun emits in days. Over the years, more bursts were detected, each showing a strange property: a frequency-dependent arrival time. Higher frequency components arrived first, and lower ones lagged behind. This effect, known as dispersion, occurs because radio waves passing through ionized gas are slowed depending on their frequency. The amount of delay encodes the total number of free electrons encountered between the source and the observer. This number is known as the dispersion measure, dm. If astronomers could pinpoint where an FRB originates, measure its distance, and determine its host galaxy, then subtract contributions from the Milky Way and that host galaxy, the remaining dm would reveal the amount of intergalactic matter along the line of sight. In theory, FRBs could map the invisible matter between galaxies. But there was one major obstacle. Astronomers had to locate each FRB precisely down to a specific galaxy. For years, that was nearly impossible. The breakthrough came with the construction of the Deep Synoptic Array 110, or DSA 110A, network of 110 radio antennas in the California desert designed specifically to detect and accurately localize FRBs. This array could pinpoint FRBs to oxycon precision, meaning it could identify the exact galaxy where each burst originated. Once the host galaxy was known, researchers could measure its distance with spectroscopy. Between January 2022 and March 2024, the DSA 110 detected 60 new FRBs, and 39 of these were precisely localized. Combined with FRBs localized by other telescopes, the sample grew to 69 well-characterized bursts, finally enough for a statistically meaningful census of baryons in the universe. For the first time, scientists had everything they needed: the FRB distance, the total dispersion measure, the host galaxy properties, and the intergalactic component of dm. What came next solved the mystery. With distances and dispersion measures in hand, astronomers subtracted the contributions from the Milky Way's interstellar and halo gas. The FRB's hosts galaxy in its local environment. What remained was the dispersion caused by the intergalactic medium, the tenuous gas filling the space between galaxies. This intergalactic DM, averaged over dozens of FRBs, gave a clear indication of how many free electrons, and therefore how much baryonic matter must exist in the vast cosmic web. The result was astonishing. Approximately 76% of the universe's baryons were found exactly where theory predicted. But where telescopes had been unable to see them, the missing matter had not been missing at all. It had been woven into the filaments of intergalactic space, in forms too diffuse to detect, except through their influence on passing radio waves. The baryons were found in the web. The FRB measurements also revealed a striking feature nicknamed the DM cliff, an abrupt drop in dispersion for FRBs located beyond certain distances. This phenomenon suggested that there is a minimum baseline density of gas everywhere in the universe. No region is a perfect vacuum. Even the emptiest cosmic void contains enough ionized gas to register in the dispersion measure. This discovery confirms predictions from simulations. The cosmic web is not merely a structural framework, it is a vast reservoir of baryonic material, stretched between galaxies and clusters, heated by feedback from stars and black holes. For decades, large-scale cosmological simulations such as IllustrisTNG proposed that most baryonic matter exists outside galaxies, in warm hot filaments forming the cosmic web. These simulations modeled gravity, fluid dynamics, star formation, and the violent feedback from supernova and active galactic nuclei. But they remained models, compelling, elegant, but unverified The FRB results changed that. The measured distribution and density of intergalactic gas matched the predictions of IllustrisTNG with remarkable accuracy. After decades of uncertainty, the simulations gained solid observational support. A major pillar of modern cosmology was confirmed. Simulations and observations now spoke the same language. Solving the missing baryons problem does more than close a chapter, it opens new ones. It helps clarify cosmological tensions. One example is the S8 tension, a disagreement between different measurements of cosmic structure. If feedback processes are strong enough to expel baryons into intergalactic filaments, as the FRB result suggests, then some models may overestimate the amount of structure that should be visible. The FRB findings help reconcile these discrepancies. It validates a generation of simulations. The agreement with numerical models boosts confidence in how we understand galaxy formation, gas flow, and the evolution of structure across billions of years. It transforms FRBs from curiosities into essential cosmological tools. In just over a decade, fast radio bursts went from mysterious flashes to powerful probes of intergalactic matter, and they may soon become as important as supernova in measuring cosmic expansion and structure. The importance of FRBs extends far beyond this discovery. As instruments improve and more arrays like the DSA-110 come online, astronomers expect thousands of localized FRBs, detailed three-dimensional maps of the cosmic web, direct measurements of gas flows between galaxies, constraints on feedback mechanisms, refined cosmological parameters. FRBs are on track to become one of the most valuable tools in the next era of astronomy, providing insights unavailable through any other method. Even with the mystery solved, questions remain. How exactly are FRBs produced? What are the detailed properties of the warm-hot intergalactic medium? How does the density of baryons vary across cosmic time? What roles do black holes and supernova play in shaping the distribution? The missing baryons were found, but the processes that placed them there demand further exploration. Science rarely ends with an answer. It continues with a better question. After decades of searching, the missing matter of the universe has been found, not in galaxies, not in clusters, not in strange exotic forms, but in the vast intergalactic spaces that bind the cosmos together. FRBs, once an astronomical curiosity, provided the key to unlocking this cosmic puzzle. Their fleeting millisecond pulses illuminated structures too faint to see, revealing a minimum density of gas throughout the universe, the architecture of the cosmic web, the accuracy of modern simulations, and the location of the universe's missing baryonic matter. The solution to the mystery was always out there, woven into the fabric of space, waiting for a method capable of detecting it. With FRBs, astronomers finally had that method. As we continue to study them, we will refine our understanding of the cosmos, uncover new mysteries, and perhaps reveal aspects of the universe we have yet to imagine. The universe has given up another one of its secrets, and countless more await discovery.